Hello everyone, this is Mr. 13 Things, and I'm going to try to go through relatively quickly here why some of us promote use of the TI-83 calculator, TI-84 plus TI calculator, at the same time, which would be called maybe old technology, at the same time we promote things like www.pacifict.com, Wolfram Alpha, old school things like MIT OpenCourseWare, but we're going to stick right now to this concept of everybody loves simple animation if it says something like this. Okay, let me see how this might work. Every now and then, you might see this on a board. Spash is number 1. Now, it might have been when I was a kid, believe it or not, the Redskins are number 1, or Marist is number 1, or it could be PJ is number 1. And everybody loves that organizationally. We like to think it, we like to do it, we like to empower it, we like to envision it. But what we like even more than Spash is number 1, or let me go ahead and put it over here. Let's not. Marist is number 1. All right? More than liking that statically, we like it when it moves across the page or goes up and down, or probably even more so if it turns and scatters. And so the reason why many of us promote use of the TI-83 is because it makes the possibility of animation of letters, pictures, and simple shapes a very quick reality. So much so that when students are playing around with it, given the time, they post things like this to the web, but students don't generally say Spash is number 1 or Marist is number 1. They say something a little bit less appropriate, as we say. All right, so let's look at, and what I'm going to go through to do here, and then hopefully in 20 minutes total, is how the theory and then the implementation of how you make something like this move around or anything like that. All right, so it starts with this general framework that anything can be broken up into points, any shape in 3D or 2D can be broken up into points and edges. Or if you want to think about it, you could think about it as nodes and edges if you really want to tie things forward in mathematics. But any shape, and you can include, I would guess, letters in shapes. Now, eventually, you're going to see that any shape can be in 3D or 2D, can be broken up into triangles. And triangles can be broken up into nodes or vertices and edges. And 3 points, 3 edges, and on and on and on. All right. So this is all predicated on the fact that any shape in 3D or 2D can be broken up into points or edges. In reality, when we're doing 2D, we actually are also doing 3D with your third coordinate being effectively 0. This becomes pretty important. If we stick nowadays with the concept of everything 2D because it appears 2D, we have missed the boat. So here's the boat, right? There's the boat. There's the boat there. And it's sailing away, and here is me and you, and we're missing it. Bye, boat. Goodbye. Bye, boat. And not B-U-Y, but hopefully we can B-U-Y the boat, but we'll talk about that at another time. So let's think about the process here. The concept is any shape can be broken into points, okay, and edges, and points are stored as vectors, right? And basically they are three-dimensional, And the minute we don't talk about that, we get eventually lost in the math. So all points are stored as vectors, and vectors are three-dimensional, and we store, and this is the key thing, we store points or vectors in a stack, a matrix that's a 3 by 1 matrix that is also called then a vector. So this is going to be the typical, the x, the y, and the z. So any shape can be broken up into triangles, or if you want to get a little bit better than that, can be broken up into points or nodes and edges, and each of those points has a x, y, and a z value. So let's do the assumption of, let's look for something common here. Let's look at the A. All right, so let's look at the A. The A here can be broken up into, right, there's the A. Effectively, later on you can see that it can be broken up to a lot less, but it can be broken up into 1. Let me see if I can change the color here. It can be broken up into a point, a second point, a third point, a fourth point, and a fifth point. 5 points. And 1, 2, 3, 4, and 5 edges. Right? 5 points and 5 edges, with the points being defined by a vector that's x, y, z, and an edge being something that's defined going from point A to point B. So you're going to see these structures are very effectively handled by using the matrix portion of this calculator. The matrix, it's also pretty effectively handled using the list portion, but the matrix portion of this calculator does a very effective job of dealing with points and edges in a format that makes animation possible. If you are going to, for instance, 1, 2, 3, 4, 5, stack up those points, and this is where it can get a little bit odd. If you're going to actually deal in 3D, you need to stack those points. We're going to go that 1, 2, 3, 4, 5. You need to stack them stacked on top of a number 1, which is called a scale factor. So we're going to do this. So we're going to call that x1, y1, and z1 on top of the number 1. This is just a consistent thing that makes a lot of great things possible. We'll talk later about some of the other links that we'll give. The concept of a 16-place transformation matrix. And so in this case, x2, y2, z2 on stack of 1. And then typically you write this dot, dot, dot. And we're going to do x, the fifth x, the fifth y, the fifth z, and then 1. Okay, so we have to very quickly realize that we have consistently for 7 or 8 years dealt with the concept of translation on a boat, or rotation on a boat, or reflection on a boat. We pretty much should not be avoiding what's going on in the games where the kids are actually translating, reflecting, and rotating things on a recurrent basis in the order of 24 times a second. So if we go with this concept that this shape here describes the nodes, and we're going to avoid the edges for right now, that we can then eventually move that shape around by manipulating it with something called a matrix, a transformation, if you would, that starts like this. It's called the identity matrix, 1, 0, 0, and then 0, 0, 1, 0, and then 0, 0, 0, 1. We have to realize that if we can describe any shape by a matrix like something like this, we can describe any transformation of that shape by transforming it using some other matrix. So this matrix is a series of vectors, and vectors are points, believe it or not, right, in 3D with a 1 chaser. And then if we want to, in this case, multiply this shape effectively by the number 1, means the shape remains the same. That's how you start. So this manipulation is the reason why many of us are not giving up on the TI-83 calculator, considering it has 0 cost if you have a computer. And otherwise, it's going to have a relatively stable cost of around either $100, or if you think about it over 6 years, or let's even say 5 years, $20 a year, a capital investment. Or if it's an emulator, it costs $0, zero incremental cost. So that is the concept here. And let me review. We'll stay within 12 minutes. The reason that we promote this is so eventually we can do stuff like this. How about this? Spash rules. Of course, it could be girls rule, boys drool, but that would be to middle school. So we can do things, and of course it won't be color for now, but adding 3 other points or vectors or values here would also get me color to any one of these typical points or lines. But we can do that in the order and within the abilities of students around, I would say, from what I've seen on the web, around 6th to 7th grade. Right? Considering students are gaining a lot earlier than that, this is not too far out there. This gives you the concept of using a calculator starting around middle school, as is oft done, and using it throughout your career so that perhaps earlier than later you can start realizing, oh, this is a little slow, and some of the tools available out at places like this are then accessible to you. This is no longer advanced technology, and it is no longer outdated technology either. You keep track of points in a stack called a vector with a 1 over the bottom. That's a scale factor. You multiply them by a transformation, and then not only can you make spash be written, you can make spash be moved and rotated in 3D space. Or, I'm sorry, keep on saying spash. Go Marist. Thanks for listening. In the next video, we'll talk about how we actually plug that in to the calculator and a little bit of theory in terms of the ability to rotate things.